Last time we were looking at section 7.3, where we are encountering repeating decimals. And we talked about how to take a fractional form and turn it into the decimal and figure out how many of the decimal values repeat. And I told you that this time what we would do is we would go the other direction. We would take a repeating decimal and we would turn it back into a fractional form. So that's where we are headed next. So example number 3 it's a fairly standard one. If you're working on like a standardized test and you see a problem like this where everything repeats, okay, the value after the decimal point, all of it's repeating. There's a bar over everything. A really quick and easy way to know how to do this, I'm going to show you because you should know in a testing environment where you're timed especially, that the reality is that this will become the number that they give you over 99. Now I'm going to show you why here in this problem, but it will. The catch is that that only works if everything repeats. So if you compare this problem to the next problem, it doesn't work that way at all. So I can't just shortcut this one. I can shortcut here. If I did this, I would be right. But if you try it over here, you're not going to be correct. So I'd like to show you how we do it in general, and it'll result in this answer on this one. And then you would reduce it if it reduces after that. So if this would have been 60 over 99, right, we would simplify and so forth after that. So how do we get to this point, and why in the world is it over 99? What's going on? Well, here's the deal. We're going to set this up to say that we have the 0.61 repeating, and it equals some number n. I don't know what n is, but it equals some number n. All right, so what I want to do is however many decimals repeat. This is the same thing we're going to do in the next problem. However many decimals repeat, we're going to multiply by that power of 10. So for example, this one has 2 decimals repeating. So that would be multiplying by 10, 10. So it's 100. So we're going to multiply both sides by 100. Okay, so when I do that, this is actually, remember, 61, 61, 61, right? I mean, that's what it is, and it keeps going. Sort of dot, dot, dot here. And if I multiply by 100, we know that moves my decimal point 2 to the right. Yeah? So this will become 61 now, but then I'm going to have the same 61 repeating in the exact same location I had it before. So on the left-hand side, I now have 61.61 repeating, and it equals 100n. So my goal is to figure out what n is. Obviously, if I divide it by 100, I'm just going back to the previous line. So that's not what I want to do. But what we should recognize is that if it didn't have that silly little 61 repeating, we'd be able to divide and I wouldn't have any repeating parts at all, correct? Well, here's the cool thing. I know what 61 repeating is. It's n. So I can actually subtract n from the side with n's on it, and 0.61 repeating from the side with the 61 repeatings on it, because they're equal quantities, right? One of the properties of equations is that I can add or subtract the same thing to both sides of an equation, and it will leave it the same value it was to begin with. They don't change. The equality is still true. But the cool thing is, because I have 2 representations for the same quantity, I affect the side with n's on it with the n, and I affect the sides with the 61 repeatings with the 61 repeating part. And then when I subtract, these pieces become 0, right? And I'm left with 61. And then on the right-hand side, what's 100n minus n? 99n, right? Subtraction, 100 apples minus 1 apple is 99 apples. And then if I divide by my 99, what do you see? 61 over 99, which is what I told you the shortcut was to begin with, right? So what I did on the left-hand side is really why the shortcut works. But it only works when everything repeats. All right, everybody good with that? Okay, ready to try another one where they don't have everything repeating. Okay, we're going to start out the same way. I don't know why I did the n on the right hand or on the right hand side on the last one. I'm just going to put it on the left hand side here. Okay, so I said on the last one, I need to multiply by whatever number repeats that power of 10. So please don't look at this and say, I've got 2 decimals, I'm going to multiply by 100. You're not. There's only one of them that repeats. So we're only going to multiply by 10 because there's only one decimal, 10 to the 1, that repeats. So again, this is 0.61111 and it keeps going, right? And when I multiply by 10, it moves the decimal 1 to the right. So it's very tempting, and I realize that it's true to write this as 6.1 repeating. That's true. It is. But I really want the repeating bars to line up. So although it's not really very natural to do so, I'm going to still put the bar on top of the second one because I want them to line up in a minute here. And the bar was originally over the hundredths place, right? The second digit. So I want it to still be over that digit. So this will become 6.11 repeating. And on the left it's 10n. Okay, multiplied by 10 because only one number repeats. But I simply wrote the number out longer. And if it helps you to write it out a whole bunch of times, you can do that. I know for some reason these repeating decimals sort of bother us. So if you want to just write a whole bunch of them out and just sort of put a dot, 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 I'm comfortable with that. I'm okay with that. It helps you to think about it better. But I'm still going to subtract n and its decimal component from both sides. Right? This is what's going on here if you think about it in long form. Parts of this match up. In particular, everything from here on, right? And when I'm subtracting, it removes things that match. So on the left-hand side, very nicely, I end up with 9n, but on the right-hand side, it's not so pretty. I still end up with a decimal. What is 6.1 minus 0.6? Yeah, it is 5.5. Still have a decimal. But again, the goal is to get n by itself in a different form. So what would I do now to get rid of the 9? I'll divide. Okay, you don't get to leave fractions and decimals intermixed in a problem. It's not going to ever be acceptable. So I need to get this so that it's not a fraction on top of a decimal on top of a fraction, or in the numerator of a fraction. So how would I get the 5.5 to be not a decimal? What would I have to do to it? You could. I think it's going to make it messier. There's an easier way to deal with it. We could multiply it by 2. On this one, that works really nicely because it's 0.5. In general, no matter what the number is, I could multiply it by 10, though. Your way is going to be faster on this one, though, so please don't hear me saying that that's not okay. You could do that, but it doesn't always work if you end up with like 0.8 at the end. So the nice thing about multiplying by 10 is that it takes the decimal and simply moves it 1 to the right. So this is now 55 over 90. And then we would reduce. So what do 55 and 90 have in common? A 5, so you can divide them both by 5, reduce them both by 5 if you prefer that language. And you would have your 11 over, what's 90 divided by 5? 18. And Hannah's suggestion, which was a really good one, I've never had anybody suggest that to me before, so kudos on that, was to recognize that on this one in particular, you could just multiply by 2 and it would solve the problem. You would have 11 over 18. So if you happened to recognize that on a specific problem, it's fantastic. Do it if you want. It just won't work on every problem. Okay? So this would be our answer in either way we did it. At that point, it's 11 over 18. Now think with me. How could you make sure that 11 over 18 is the right answer? Got it. Take your calculator and check it out. 11 divided by 18. Does it equal 0.6111111? That's what you'd be looking for. And as long as it did, then you know that you did get the right answer. Hopefully you did the process right and you didn't just make lots of mistakes along the way that ended up the right answer. Happens sometimes. You guys laugh, but I'm telling you. I wish I could just look at the answer sometimes and know you did it right. It doesn't always work that way. But that's what we would get, is 11 over 18. Okay, so I have a cool fact to show you on the next example. Okay, you ready? All right, so the first time that I encountered this realization was actually in a high school classroom. Myself, I was in high school, and an acquaintance of mine was totally arguing with the teacher. And the teacher showed what I'm about to show you and just blew the girl's mind. And the girl still felt like there was some funny math going on there, still could not be the right answer. So I want to show you this because it is really cool, and it's a good fact to know because it's kind of one of those funny little tricky things that can show up again on like a standardized test that if you just knew it, you'd just be able to answer it and move on. And it's kind of an interesting fact. We're going to do the same thing on this problem that we did on the last two problems, all right? We have the decimal, which is 0.9 repeating, and we're going to figure out what it would be in fractional form. So I have n equals 0.9 repeating, like so. And I'm going to be multiplying powers of 10. Will I multiply by 10, 100, 1,000? What will I multiply on this problem? 10. There's only one number repeating, so I only need to multiply by 10. So on the left, it's 10n. On the right, what will it become? Right, 9.9 repeating. Everybody good so far? Okay? And then when I get to that point, I have to do subtraction. That's always what comes next. I subtract the original statement I started with. It's always the original statement too, by the way. You're always just subtracting your first line. Minus n on the left, minus 0.9 repeating on the right. So what is 10n minus n? 9n. And what is 9.9 repeating minus 0.9 repeating? 9. And then what? It divides by 9, so what's n? 1. So here's what you just showed, right along with me. These are exactly the same, and it's true. They are. Because the 9s at the end never stop, right? If they did, they wouldn't be equal. But the 9s repeat forever, and that's actually equal to the quantity 1. It's a very interesting fact. You're going to see another example of this or a question involving this in your homework, but I'll hold off on trying to spoil all the fun until you get there. All right, let's take a look at another one. Oops. This one's asking us to find a decimal between two numbers. Now, the reality is that you know what 0.9 repeating is because we just did this problem. So if I have this value and I know it differently, what is 0.9 repeating again? 1. How could I find a value between 1 and 1.1? Okay, that would be one of them. If you feel comfortable enough, this one's not so bad because it is sort of money-like, right? It's $1 and it's $1.10 kind of thing. 1.02 would work. What if you wanted to find the number? Oh wait, I've got that for part B. So this would be an answer. Part B. What if you want to find the decimal halfway between? How do you find that? How do you in general find a decimal halfway between any two numbers? Yes, you do. And then what do you think you might do? Divide by 2. It's the exact same thing that you guys do when you're trying to average your grades in a class. In particular, if all the grades are worth the same amount, you add them together and then you divide by the number of grades, right? It's the same thing. If you're trying to average things, find their halfway point between them, you add them together and divide by, in this case 2, because there's 2 decimals. You'll get 1.05 here, right? everybody got 1.05? Yeah. Now, you might ask yourself, okay, well, that's really nice, but I mean, we already knew that the 0.9 repeating was 1. What if it had said 0.5 repeating? I mean, what if I did that, right? What would I do? Well, there's a couple of things you could do. So one thing you could do is you could turn it into the decimal form, or the fractional form over here like this. You could do that. And then you could add two fractions together and divide by 2. Maybe not the easiest way to do that, but you could do that. All right, what else could you do? Well, you could take, let's say, for example, again, that it said 0.5 repeating like this, and maybe even 0.6 repeating for fun, two numbers that are both repeating. So there's a couple things. Again, we could turn them into fractions and go with that. You could also just add a bunch of them together. Okay, hang on. So we realize that, of course, this is a approximation because I've stopped it, right? But if you're simply looking for numbers between them, like on part A, well, what's between 0.55555 and 0.66666? You might just pick 0.6, right? This is kind of like thinking about it as 55 cents and 66 cents. What's between 55 cents and 66 cents? 60 cents or 62 cents or 55 or 56 cents. Any of those would be fine. For part B, if you're thinking about it, you could actually add them together. I meant to do that as a comment between those, sorry. You could add them together and divide by 2. And if you use enough decimal places, and I'm not going to clarify exactly what I mean by enough, just use a bunch of them in your calculator is what I mean, and divide by 2, it'll still give you an approximation for something that's going to make sense. So just for kicks and giggles, try this one for me. What happens when you do a whole bunch of 0.5s, a whole bunch of then 6s, and divide by 2? What do you got? I don't feel like you divided by 2. Did you add them or did you subtract? Okay. What did you get though, Brooke?
After dividing by 2 and everything?
Yeah.
0.6.
Oh, sorry. I was hearing yours. You're in the wrong place. 6, what did you say?
1105.
Okay. So I think if you use more decimal places, you'll find out on this particular one that the 1's going to keep repeating. So I believe that you're going to get, I totally made this number up on the spot, but I think you're going to get that 0.61 repeating that, oddly enough, was quite similar to something I just did a minute ago on this one. Okay. But if you use several decimal places, you can find the halfway point the same way that you would with decimals that terminate. Okay? All right. We actually encountered a question in our review of your last, or in the questions you're asking about your last section, that's quite similar to this particular problem. This question reads the following: some addition problems are easier to compute with fractions, and some are easier to compute with decimals. For example, 1/7 plus 5/7 is easier to compute than 0.142857 repeating plus 0.714285 repeating. You agree with that statement, right? Okay, good. And then 0.4 plus 0.25 is easier to compute than 2/5 plus 1/4. Do we agree with that statement as well? Yeah. So it says describe situations in which you think it would be easier to work with fractions than decimals, and vice versa. So, 2 questions. All about it's easier if or when. So when is it easier to work with fractions? What kinds of things do you notice with their examples? When do you think it would be easier to work with fractions? I agree. Same denominators, super helpful, right? Same denominator is a very helpful thing with fractions. We'll just kind of keep in a tally. Anything you can think of to add into the decimals category? When is it easier to work with decimals? Okay, so potentially if there were mixed numbers involved, sure. What else?
Dealing with money, what you're talking about.
Okay, so if we were working with money, we might want to choose, in fact, because of the visual representation for us, decimals to work with, yeah?
I think with fractions, if you don't have a calculator available, but I don't know.
So like, you think it's easier to work with fractions when there's not a calculator? So fractions, calculators are not the friendliest with fractions. Would you?
Yeah, I would have said I would rather work with decimals if I don't have a calculator.
Okay.
Because I can line up the decimal points and add them that way. If I do a fraction without a calculator, I have to find common denominators.
Okay.
And they get bigger.
Okay.
That might be harder without a calculator.
So this statement could be in either category depending on how you think about it.
I like fractions better than decimals.
I like fractions better decimals too. Nobody's mentioned one of the glaring things that occurred in these examples over here. Yeah, non-terminating. So there's repeating decimals. That's what you said, right, Summer? Sorry, there's a lot of background noise with the street out there today. Yeah, when decimals are repeating, they're not easy to work with. So over here, fractions are easier with, or let's say when decimals are repeating. How about I say when the decimal form repeats? And, or we could have likewise written underneath the decimal part, is that decimals are convenient. So like even with what you were saying, Brooke, the decimals that you were thinking about, though you didn't say it, were terminating decimals, weren't they? Lining things up and adding together. Because like, I mean, we can line things up with the repeating ones and add them together, but like that's awkward and weird with that one because they don't actually match up. Like if you had, for example, this number and this number added, we'd do okay because they're the same, right? It's just like multiplying by 2. But when they don't match, it's not easy. So you could either write it like we did underneath the fractions part or underneath the decimal parts, you could write when they terminate. And this is similar to the one that you guys did that last question of, was it C4 or something like that on the last section, where it was asking questions of when it's easier to kind of think about fractions versus decimals. But this one's specifically about adding. Any questions on that? Nope.